Right, so we got the yield from one, and then the yield from the second ingredient, which is going to be 43.0. So we're going to go with 43.0 grams of KOH, and convert that to moles. It's going to be a mole of this KOH weighs 56.11 grams. So the grams of KOH cancel, that leaves us with moles of KOH. And then this is a 2-to-1 mole ratio, right? And so 1 mole of K2CO3 for every 2 moles of KOH. And then the molar mass of K2CO3, 138.21. 21 grams of K2CO3 per mole. K2CO3. Everything cancels. Is that what other people got? Yep. And so how much are you going to make? In theory, how much are you going to make? Yeah. We can only make this much. Because once we make this much, then all the CO2 is gone. We only have 15.6 grams to start with. And so there's no way we can make that much there. And so the smaller amount is going to be theoretical yield. This is the theoretical yield. And therefore, 15.6 grams of CO2, this is called the ER or the LR. The LR. The LR is completely reacted. So once we react all 15.6 grams, we're stuck at 48.99. We aren't going to go any higher because there's no more CO2 left. Although there is going to be KOH left. KOH is called our excess reactant, or ER. Thing is, this is pretty close, you know. They have pretty close to the same yield, so we just have a little bit of KOH left over. And so what we're going to do is we're going to figure out how much KOH is left over. So that's the fourth calculation here. The excess reactant remaining. The excess reactant remaining, what was the equation? This is equal to the initial. How much was the initial?
43.0
Minus the amount consumed by the limiting reactant. So how many grams of KOH were consumed by LR? And so why don't you do the calculation? You already have it? 39.77. I'll set it up then. 43.0 grams of KOH initial minus the grams of KOH consumed by the LR. We always start off with the limiting reagent. What was the limiting reagent again?
15.6 grams of carbon dioxide.
15.6 grams of CO2. And then we're going to go to moles. Actually, I'll just map it out like this. So we'll go from grams of CO2 to moles of CO2. From moles of CO2, we'll go to moles of K2CO3. And from moles of K2CO3, we'll go to grams of K2CO3.
Are you going to moles of potassium?
Oops, no, you're right. I'm headed the wrong direction. I want to go from moles of CO2 to moles of KOH. And from moles of KOH to grams of KOH, the other reactant. That's right. And so what did this number come out to? Minus?
Came out to 39.77.
39.77 grams of KOH consumed. So this initial minus the consumed, which means how much is going to be left over?
3.23 grams.
What is it?
3.23.
3.23 grams. In other words, 3.2 grams unreacted. Unreacted KOH. All right, this is a typical limiting reagent. The other problems here. Okay, I need to back up a little more. The other problems are going to be like this. For example, you're only given one ingredient. So we need copper and silver nitrate for this. This is single. Is this single replacement? Yeah, this is single replacement type reaction. Copper and silver nitrate. And so we're given the copper, but we aren't given the amount of silver nitrate. Instead, for the silver nitrate, they say excess silver nitrate. And so the limiting reactant's got to be copper here. The other one's an excess. Take a look at this one. Soaps, this is soap production. Soap production, this is an example of metathesis reaction here. The last compound is soap. Calculate the number of grams of sodium hydroxide required to produce 323 grams of soap by this method. And so here we're just interested in the sodium hydroxide. That means we have plenty of this to react with that. Over here, according to the reaction, how many grams of carbon tetrachloride are required for a complete reaction? So this one we're just doing. And so these typically we don't worry about, limiting reactant if we're only getting one ingredient. We assume the other is an excess or just the right amount. All right, let's skip that for now, and then what we're going to look at is something called percent yield. Actual yield and theoretical yield. This is the actual. So let's say we go through the ingredients, and let's say in theory, we should be able to make 100 cookies. Let's say that's our theoretical yield, considering all the ingredients. This came out to a smaller amount, 100 cookies. Theoretical yield. But that's not always the number of cookies you're going to get. In theory, you should have been able to get 100 cookies based on what the limiting reagent is. But sometimes you have losses. And so, when you actually do this, there could be losses. Losses may occur. For example, you might drop a cookie on the floor. You might not want to eat it afterwards. Or you might eat some cookies before you drop them. And so you might have some losses. Let's say, even though in theory, your actual yield of cookies came out to 95 cookies, but you had enough ingredients to make 100 cookies, and so you lost 5 cookies. And so what we're going to have is we're going to have something called the percent yield. The percent yield is you got 95, you're supposed to get 100. Times 100%, and so this is a 95% yield. So this is called determining percent yield. And then we have using percent yield. Armed with this knowledge here, you can make some predictions. And so let's say, the last time I made some cookies, I only got a 95% yield, so I lost some. And so when we use percent yields, we could do A, predict actual yield of product. So let's say the next time I'm going to make cookies, I'm going to plan to make 200 in theory. And so an example of this would be, let's say my theoretical yield for 200 cookies, but based on my last batch, I'm probably only going to get, out of this 200, I'm probably only get how many? 190. And so in this case, we're going to expect an actual yield of 190. Probably going to lose about 10 of them. This is a guess. Could be more, could be less. But based on the last batch, this is what I predict. And so what we're going to do is this. We have a 200 actual yield, and then the percent yield is going to look like this. It's going to be 95. Oh no, this is not actual, this is theoretical, sorry. 200 theoretical yield, and it's going to be 95 actual yield over 100 theoretical yield. So that's how we're going to calculate 190 for our actual yield. Or B is to calculate the ingredients required. In other words, the ingredients required to obtain a desired actual yield. Let's say I don't want 95 cookies. Let's say I want 100 cookies actual yield. It's for an event. And so the example here was, I want 100 actual cookies. How many should I plan to make? Or how many should I buy? Let's say I need 100 cookies, but if I end up losing 5%, and I only get 95%, how many should I buy? Well, if I want 100 actually, then for every 95 I actually get, I better order 100. Because I'm going to lose 5 out of 100. So what does that come out to? Well, I want 100 times 100 divided by 95. 105.26. So I better plan on making 105.26 in order to get 100. Or if I'm going to buy it, I better buy 106 cookies in anticipation of losing 6. And so this would be the number I need. And so let's do examples of these 3 types of calculations. Let's take a look at this first one. The function of sodium thiosulfate. Sodium thiosulfate is, this is sodium ion. Thiosulfate is S2O3 2 minus. Thiosulfate is actually a common ion, but I didn't have you memorize it. And so we need 2 sodiums to balance out the thiosulfate. Is used to remove excess silver bromide. Well, here's the silver bromide. So the sodium thiosulfate reacts with silver bromide. This looks to be an AB plus CD reaction. AB plus CD is called what? Double replacement. Are those the products you would have predicted for double replacement? let's see, we would have predicted sodium bromide and silver thiosulfate. Did we get silver thiosulfate? What is that? What this is an example of is two things. One, it's incomplete reaction, but it is complete in the sense, it's incomplete in the sense of double replacement. Or two, this is called a mixed cation salt. And this is why I like to call it metathesis. In metathesis, this works for metathesis. This doesn't work for double replacement. This works for metathesis because this product here requires 3 sodium ions, 1 silver ion, and 2 thiosulfate ions to come together to precipitate. This is actually precipitating here. And so metathesis, it fits that category because all we're doing is mixing up the ions and seeing what's favorable. It turns out that, which we haven't learned how to name, is favorable. Favorable ion combination. How about this? This appeared in one of the homeworks, Fe3O4. You recall seeing this in the homework? How would you name this? Well, this is called magnetite. It's a mineral. It's a magnetic mineral. It's black. Magnetite. But that's its common name. What would you name this? Would it be iron 3 oxide? Iron 2 oxide? No. Iron 3 oxide, rust, looks like this. It's Fe2O3. Iron 2 oxide is FeO. So what is this? Iron 4 oxide? No. Well, we have how many oxides? We have 4 oxides, each -2, so this gives us -8. How many irons do we have? We have 3 irons. These 3 irons cumulatively have to give us +8 because +8 plus a -8 is going to give us 0, the charge on the compound. And so that means each iron is, if I have +8 distributed over 3 irons, then each iron is +8/3. +8/3. +8/3. And so +8/3 times 3 is going to give us +8. So this should be called iron 8/3 oxide, right? Iron 8/3 is funny. So 8/3 we can reduce to, is that 2 and 2/3? And so we should call it iron 2 and 2/3 oxide. Is that right? So it's lost 2 and 2/3 of an electron. Each iron. No? No, that's wrong also. So how can you fix this? Yeah. Geologists would be happy. Magnetite. Important mineral. Especially in lava, you know, magnetite, it's frozen in lava, so you can see, you know. When the magnetite got frozen, it was oriented towards the North Pole.
Is it magnetic? Is it magnetic?
Magnetic, yeah, magnetite's magnetic. Forms little crystals. So does somebody see how we can fix it? What are the charges on iron? Iron 2. So if we had 3 iron 2s, are we enough? No, we're not enough. We gotta go to +8. Oh, well, what if we're iron 3? If we had 3 iron 3s, then we're at +9. It's too much. So 3 iron 2s is not enough. 3 iron 3s is too much. And so can you think of something we might be able to do? Well, how about this? Not 2 iron 2s, and one, because if I take 2 iron 2s, that gives me +4, and 1 iron 3, give me +7. How about this? Let's take 2 iron 3s and 1 iron 2. If we take 2 iron 3s and 1 iron 2, that's going to give us +8. +8, that'll nicely balance out. And so it's not 2 2/3. What it is I'm going to have 2 iron 3s and 1 iron 2. This is an example of mixed cation salt or mixed cation compound. Just like this, you know. Over here I have mixed cations. I just don't have all one cation. This would be Na4. But if we remove one of those sodiums and replace it with silver, get this. This turns out to be a stable compound. And so this is the reason why I use that funny name, metathesis. I use metathesis because sometimes the double replacement doesn't predict it. So we look for forming stable things. But anyway, let's take a look at this. What is the percentage yield if the reaction of 8.18 grams of sodium thiosulfate? So they tell us how much sodium thiosulfate we have, but they don't tell us how much silver bromide. You know, sodium bromide, but no silver. So what we do is we automatically assume that this sodium thiosulfate must be the limiting reactant, and silver bromide is either in excess, or stoichiometric. And so our theoretical yield is just going to be based on this reactant. And so what we're going to do is we're going to take our sodium thiosulfate. Well, isn't this the theoretical yield here? 2.61 grams of sodium bromide? What do you think that is? This is the actual yield. The actual yield is going to vary depending on who does the experiment. So somebody might get 2.61, another person might get 2.58, another person might get 2.4, depending on how much you lose. But this would be the actual yield. So what we need to do is we need to figure out, in theory, how much sodium bromide should we have produced, and let's compare it to this number. And so, there's only a step 1 here. We already know what the limiting reagent is. And so step 1 is just to predict the yield of sodium bromide here. So we start off with the limiting reagent, 8.18 grams of sodium thiosulfate. Go from grams of sodium thiosulfate to moles of sodium thiosulfate. Moles of sodium thiosulfate to moles of sodium bromide. Moles of sodium bromide to grams of sodium bromide. And so in theory, if everything were ideal and you didn't lose any, we should have gotten 2.66 grams. Well, they only got 2.61 grams, so they only lost 0.05 grams. Well, a loss of 0.05 grams is not that bad. That's pretty good, actually. 0.05 grams. Yes, it's something, losses are typical. You don't want to scrape every little piece, every little speck out of the test tube. It just takes too much time. So you get the bulk of it, the rest you don't worry about. And so actually this is a pretty good percent yield, because 2.61 grams of sodium bromide was what they actually got. In theory, they should have been able to get 2.66 grams. So it comes out to a 98.1% yield. And so this is a determination of a percent yield. Okay, that's a case where we're only given one reactant. If we go back to this one where we're given two reactants here, the barium chloride and the sodium chromate, when we did the barium chloride and the sodium chromate, we saw that the theoretical yield was 1.98 to 3.75. Was the theoretical yield. Well, it's a smaller amount, 1.98 grams. So in theory, this reaction with these two ingredients should have yielded 1.98 grams. Now, it depends on the experimenter. Some experimenters are going to get very close to that because they're extremely careful and they spend a lot of time. Others are not going to waste as much time or spend as much time. They'll get smaller yields. And so one experimenter might get like 1.5 grams. Another might get very close, like 1.97 grams. And the percent yields are going to vary. But it's up to the experimenter. Sometimes what you do is you just figure out the average. You know, what is the average percent yield for this? If we figure out some kind of average or base it on the last batch, you know, like we did with the cookies, then we can do the other calculations. And so let's take a look at the other calculations of the percent yield here. These would be the other calculations in this case. Calcium cyanamide is a common fertilizer. When mixed with water in the soil, it reacts to produce calcium carbonate ammonia. So this is a very unusual anion, CN2 with a -2 charge. Well, when that's mixed with water, this is an example of a Lewis acid-base reaction that forms calcium carbonate ammonia. How much ammonia can be obtained from 7.25 grams of calcium cyanamide in a laboratory experiment, which the percentage yield? So what they did was they just came up with some kind of average percent yield. This is the average percent yield that most people get, 92.8%. So factor in this average percent yield, you know, what is the actual yield of ammonia that we're going to get from that. The other type of calculation is shown here, and then I'll talk about, we'll do both. The Haber process for making ammonia from nitrogen in the air is given by the equation N2 plus 3H2 yields 2NH3. Calculate the mass of hydrogen that must be supplied to make. Okay, so we want 500 kilograms of ammonia actual yield. If we know that this reaction has an average 80.8% yield, then how much ingredients, you know, how much should we plan on making? We should plan on making more than this. We're going to lose 11.2% of it. So that's the other type. So we'll do these after. We'll take a break for right now and we'll do these after.